So my name's Andrew Siegel. I'm a scientist here at Argonne. One of my roles is the Director of Applications for the Exascale Computing Project, which you no doubt have heard of. Doug is actually going to give a comprehensive talk, Doug Cothey, the director, a little bit later. We're kind of backwards. I'm going to talk just about application development, and I'm not going to try to say everything. I'm going to focus on a few key ideas and put them in context to give you a sense of where we are and what we're experiencing in the project. So I'll start very, very simple and say what our goal is. Well, at a very high level, the goal is to ensure that exascale machines impact the DOE science and engineering mission. It's a very simple thought, but if you want to put it in a very distilled way, that's what we want to accomplish. And the approach is an unprecedented investment in the entire development lifecycle of applications well in advance of the deployment of the exascale machines. So I think we're all on the same page about what the goals are, and it's very simple to understand. That has several components to it, and one of them I think is a major misconception. That's one of the things that I experience every day and have for the past 3 years, and that's the idea that we're sort of porting codes to exascale machines. Of course, porting doesn't have any rigorous definition, but I'd say I would not think of it that way, depending on how you think of code porting. I would say anything that looks like, changing the order of loops and repacking data structures and, updating versions of libraries and so forth is a massive oversimplification of all of the work that's going on. I would think of it more as very significant algorithmic restructuring with a lot of new ideas behind. And this could be things like communication avoiding algorithms for sparse linear systems, just a whole range of maybe synchronization avoiding algorithms, a whole huge range of things that go much deeper than the notion of porting a code. New numerical approaches could be things like going from continuum to particle methods, or from deterministic to Monte Carlo methods, and then even things like alternate choices of physical models. So a lot of people reason backwards, and this is a whole other talk, and there's a lot of really interesting content when you take a step back and look at it, but people are asking what the machines are good at and thinking of new physics they could model that maps well onto what the architecture provides. So I think in general, the hardware is having a significant impact on all aspects of the simulation strategy. And the number of people that are involved in taking any one of these codes and trying to get them to produce what they wanted to produce on an exascale machine efficiently is kind of mind-boggling. And I'll go through a few case studies to give you a sense of how many collaborators and how many different types of expertise are necessary to accomplish what we're trying to accomplish. So that's a very big picture. I'll say what the portfolio of applications look like. And I'm actually going to go through each one just a second each to give you a flavor of the breadth of science and what we're focusing on. It's a little interesting coming after Rick's talk, where everything was about the future of AI versus what people are actually doing right now, where there'll be AI components to these things, but largely it is solving differential equations, which are the fundamental governing equations of physical systems. Okay, so I bin them in these application categories, and there's always like one that doesn't quite fit the bin, and I guess there's no perfect categorization, but here's how the 24 application projects are spread across the different categories. So we have 6 chemistry and material applications. That's also going to include quantum chromodynamics, which doesn't quite fit, but it's small stuff. Energy, mostly energy generation, so forms of energy generation facilities which are not mature enough and for some reason or another could be made more cost effective or more robust. Earth and space sciences. Then we have a bin of applications which are sort of non-traditional HPC applications, which are based more off of data analysis and machine learning and not so much on traditional solution of differential equations. And then we have national security applications. So that adds up to 24 projects. And of the 24 projects, this includes 50 plus separate codes. So there's not one code per project. In fact, many of the projects, what they're doing that's novel is combining or coupling disparate physics codes to be able to simulate at higher fidelity whatever they're trying to simulate. So it could be neutron transport and fluid dynamics, or it could be core and edge physics in a tokamak. But whatever it is, probably 5 or 6 of the projects have multiple codes involved. So we get to a total count of 50. Just a few things about them. I always take account when I'm reviewing each of the projects who still has Fortran, because there have been a number of cases of migration even during the project of Fortran to C++. I'd say we're still about a third Fortran, okay? And when I say C, I mean C++. So that's my best estimate based off, it's not counting lines of code or anything that exact, but just numbers of codes and my knowledge of about, you know, which ones are dominated by Fortran. When the project started, almost all the codes, with maybe 2 exceptions, were MPI codes or MPI with OpenMP. In many cases, the OpenMP was in a branch that kind of worked, and you had to sort of dust it off. And a lot of the codes, you could just run an MPI rank per core, often because the main data structures were being decomposed anyhow, so there was no real benefit in doing shared memory on a node. So that's where everybody started in 2016, just to give a sense. And a big component of the project that I'm not going to talk about in any detail, but you'll hear from Doug, and it's important to be aware of, is that there's a very well-defined and evolving and complex relationship between all of these application development projects and the software technology component of ECP, who are providing everything from system software up to application level solvers, for example, libraries in general, that these codes are depending on. And managing those dependencies and minimizing risk in their presence is a major component of the project that I won't talk about. Okay, so what defines an application project? 4 years ago, when this project started, we had probably 120 or so expressions of interest from different application groups. And what we asked everybody to do was to imagine a scientific or engineering exascale challenge problem that was impactful in their community that could not be done on current resources. And we also asked for detailed completion criteria for executing this problem on an exascale platform. Because this is a DOE project, we have to be able to measure performance quantitatively, and we have to be able to say what it means for a project to have succeeded. And in many cases, that also came down to a figure of merit which quantified the performance improvement of the code on the exascale system relative to the baseline system. Okay, but it's important to realize that almost every one of these projects involves significant new physics capabilities. It's not taking the exact same code and running it at finer resolution, running it with more particles, or running it faster, right? And that's always been the history of HPC with these applications, is when there was hardware with new capability, new memory, and faster processors, people imagined new physics that they could include, new effects that they hadn't modeled before, as well as refinements to how they were modeling what they were modeling originally. Okay, so I think it's important to realize that there are a lot of moving parts. It's not just the hardware, not just the programming models, not just the libraries, but actually the codes themselves are moving parts within the project, right? And that creates a very complex environment with which to track and ultimately achieve success. Okay, so that's very high level. I'm going to give a very quick flyover. I'm not going to talk about the national security applications because I'm never sure how much I can say, but I'll give a quick flyover of what the areas are. Okay, and there'll be a little image with each one that's just meant to evoke an emotional response. It doesn't really have any content to it, but I just want you to see what the areas are, and you can look at this later. I could say it very fast. I won't take much time. So ExaWind, that is looking at grids of wind turbines. So not the performance of a single wind turbine, but arrays of wind turbines in a wind farm. It's a very complicated CFD calculation interacting with structural mechanics. XSMR small modular reactors, coupled Monte Carlo neutron transport. WARP-X is plasma wake field accelerators. MFIX-EXA is carbon sequestration by something known as a chemical looping reactor, NETL, if anyone's ever heard of that. Pele is looking at combustion, particularly for reactivity control compression ignition. WDMAP is magnetically confined fusion in a tokamak. So those are the energy applications. WARP-X is kind of the outlier. It's not really energy generation. The other 5 are energy generation facilities that are either poorly understood or can't be scaled up economically. And the simulations are intended to bridge our knowledge, our gap in a lot of the knowledge of those facilities. Okay, I'll hurry up. So QMCPAC is electronic structure, XAAM additive manufacturing. Then we have quantum chromodynamics. Then we have 2 quantum chemistry codes that have slightly different scientific goals and slightly different emphases on methods. Those are NW-ChemX and GAMES. And then EXALT is molecular dynamics, but it's molecular dynamics informed by quantum chemistry and machine learning in particular, and the generation, if anyone's heard of what are known as SNAP potentials. So, but it is a molecular dynamics code. Then we have climate, subsurface geochemistry, so it's sort of wellbore integrity, fission bore modeling, crack propagation. Exostar is astrophysics, Exosky is computational cosmology, and EQSIM is earthquake predictions, so seismic modeling. Okay, I go over them all because it's kind of mind-boggling the number of areas that people are doing incredibly high-end simulation work in, and to sort of see each one gives a good flavor of what's going on. Okay. Oh, I'm sorry. The fourth group, data analytics and optimization, is kind of a mixture of slightly non-traditional things. So power grid simulation, XFEL is the free electron laser, so it's doing real-time imaging from the light source, all the processing that has to happen to the images in real time to be able to understand electronic structure, for example. Exobiome is metagenomics, so it's the processing of huge databases. And CANDLE, which Rick alluded to earlier today, is machine learning for cancer diagnosis, and that's more traditional image-based machine learning. Okay? So that's the portfolio of the non-national security applications. And I wanted to talk a little about where we are in the trajectory of the project. And the easiest way is to look at these kind of 4 high-level milestones starting last year. There were ones in previous years also. And they form kind of part of an annual cycle where I do reviews of each of the projects and address the key themes that are in each of these. And I'll just say, last year the idea was to assess application status relative to their challenge problem. So what physics did they need to develop? What codes did they still need to develop to be able to address the problems they wanted to be able to address? This year, which we're undergoing the reviews right now actually, we just did half of them, and some of my perspectives of where we are will come from those reviews. We're looking for early results on Summit or Sierra, or something that we can consider a pre-exascale architecture, something that looks like a multi-GPU node, or that is of the 100 or 200 petaflop variety. So we have 2 machines right now that match that. And so we want to see what people's performance is, what their performance bottlenecks are, what the key challenges are, how their plans have changed knowing what they know now. And it's a period where a lot of teams who sat on the sidelines probably longer than they should have, are now all in with the deployment of Summit, right? So everybody has results and work to do and new approaches that they have to pursue and new ideas based off of everything they're learning. The next review will be a more targeted mapping of the applications to one of the 2 exascale architectures, either Aurora or Frontier, because in this particular project you have to meet your figure of merit goals on one of the 2 architectures. Many will do both, but you have to do one. And so a more detailed performance analysis understanding what needs to be accomplished to get where they need to go on the particular architecture is going to be what I'm looking for. And then we expect early results on exascale hardware, honestly probably earlier than the FY21 Q4 goal, but that's what I'll be looking for. And then a demonstration of the execution of the challenge problems, meeting the figure of merit at the end of the project, and the project wraps up at the end of the 3rd quarter in FY23. So this is a broad trajectory of where application development expects the projects to be along their performance and science challenge goals over the next 3+ years. Okay, so I'll mention a little bit more to understand what I just said. When the project started in 2016, there were a number of platforms that were sort of the 10, 20 petaflop variety, which we consider the baseline platforms. So the projects that were accepted into ECP all had to have baseline performance numbers for either their challenge problem, or if they didn't have enough capability to execute it, some substitute for their challenge problem on one of these machines. And I squared off the open science machines because that's what most people are using. Right now, the current ECP focus is Summit, and of course there'll be Perlmutter soon, and Crossroads, and these are the sort of order 100 petaflop machines. So that's our current focus. And these, from the ECP perspective, although in and of themselves people are using them to do all sorts of important things, there is sort of the bridge to the target exascale platforms, which are Aurora, Frontier, and El Capitan will come, I think, a little bit after the end of the project, but I put it down anyhow for completeness. And that's sort of those are nominally the exaflop machines, okay? So everybody has to have a performance baseline that is defensible on one of the baseline platforms, and it is scaled properly to the peak theoretical performance of the machine, and that's what we use to calculate the ultimate figure of merit ratio that determines their success. Okay, and I'll just give a flavor of where we are. So what are you looking at? We keep a dashboard as part of the progress tracking of all the applications where they enter their current, what is called KP1 value. What is that? That is a ratio of their current best figure of merit calculation. Usually that's on Summit or Sierra right now, relative to their baseline. And there are two numbers. The darker blue is what they've actually measured. And the lighter blue is if we projected that out with perfect scaling up to all of Summit, for example. And the reason we have that is because oftentimes people don't have the full system number only because it was not available. So they couldn't gain access to the full system. That said, it's in no way a trivial exercise to scale up to the entire system, so it is what it is. It just gives a sense of if they were able to scale, where they would be. And you see we have numbers all over the place. I'll talk about a couple, Exalt, where this is actually above 50. This is, the projected value is 90. And I'll sort of explain why and give a flavor of some of the things they did to get to that point. And we have other projects where the figure of merit improvements have been smaller than might be expected. I think it's hard to take these numbers as precise indications of anything, but if you're in the 7 to 10 range, you're doing well. If you're beneath that, you're probably behind, and if you're above that, which we are in a number of cases, it's better than would have been expected based off of the improvement in hardware. But this just gives a sense of kind of where people are, how we measure where they are, and what work has to be done going forward. Okay, so then I do this every year, and I just updated this last night based on this year. And I go back 2 years, it would look different. Last year, it would look different. And what I do is I take a look at all of the projects and where they are right now, and I say, what are the top 5 or 6 common challenges that they're all facing and getting on exascale platforms? Even though it's gone well in some cases, actually much better than I would have thought, everybody still has a number of difficulties and challenges. So the first is probably the most obvious, and it might be true of a fourth of the codes, and that's just that they have very flat performance profiles. So there's not the obvious 80-20 rule or the 2 or 3 numerically intensive computational kernels that you could easily port to a coprocessor and refactor and try to get performance. The performance is kind of all over the place. There might be 20 routines that are 5% of the performance or so. And so that's a problem. It's always a challenge for accelerator architectures. And there are ideas to address it, but it takes longer and they're further behind because of it. Another big issue, which I'll say a few things about, which surprised me a little bit, came up a lot at the recent reviews, is the nature of strong scaling on systems which have to be heavily subscribed to achieve something close to peak performance. So if you think of n sub 1/2 for a GPU versus a CPU, it's relatively high. That's how the GPU works, right? It masks latency by being oversubscribed with work and scheduling the work very efficiently in hardware. So what does that mean? Well, that's great if you have a single GPU, but if you want to spread a fixed amount of work thinner across a network of GPUs, then you're going to peter out in your strong scaling plot earlier than you would on a CPU. And Paul Fisher and company just wrote a paper on this, and the results are kind of startling. It's not necessarily all bad. A lot of people include physics proportional to the improved performance of the machine, but strong scaling is important. It's important because work is linear in time. And if you have a machine that's 100 times faster, you could say, I can do in a day now what it took me 100 days to do before. And that's a powerful statement versus things like 3D grids where you have a factor of 16. If you have a CFL number times 2 cubed, then you say, well, I cut the grid in half, but I have to do 16 times as much work now. So, it doesn't tell as powerful a story about the improvement of, and of course, computational chemistry can be anywhere from n to the 4th, n to the 7th. in terms of the number of bodies. So things that are linear tell powerful stories about the impact of new hardware, what you can actually do with the code. So I consider strong scaling important, and a lot of people are having trouble, and that came out of the last set of reviews. Another big issue is, people run on GPUs, they don't know what to expect, right? So yes, we've all dealt with a roofline model for a generation, and you can use roofline on GPUs. A modified, more sophisticated version of the roofline is better, and there are ways to do it, but people aren't very sophisticated at it, so they kind of run and they don't know if they're doing well or not, and they don't know how to tell if they're doing well, and they're not quite sure what to compare it to, and it creates a sort of additional sense of confusion versus what we're used to doing for a long time. So I'd say just understanding whether they're doing well relative to what their algorithm could do and why or why not is behind. Of course, we heard about the zoo of programming models. It's all over the place. People use CUDA, OpenACC, they have OpenMP 4.5, and Siegel, and HIP, and we have all sorts of things, and it's not quite clear to people moving toward the exascale systems what they should focus on or how they should manage risk in the context of all these moving parts. There's a lot of issues of looking at the architecture and saying this architecture looks good for high flop to load ratios. That's true of all architectures, but it looks good at things that don't have significant divergence in them, or whatever it is. Let's do electron subcycling, or let's do localized physics for subgrid models. There's a lot of this idea that what's available is going to dictate kind of the next thing that we prioritize to do in terms of physics modeling, because we don't want a poor algorithmic fit to the hardware. So I wouldn't say that's a challenge, but I guess it is a challenge. It's one people I think are overcoming, but it's still in the forethought of many people's R&D agenda. And the last one, which we're managing partly in ECP and also with the community as a whole, is just software dependencies. Everything from system software up to application level libraries. What's going to be available and what's going to work. Because a lot of HPC codes in the last 10 to 15 years were not like the ones when I started. You built it off of PETSI or Trilinos or Hypera or something that you're assuming is going to be there and is going to perform well when you get to the machine. And that's a difficult assumption. In the old days when we started, you did everything by yourself. And that was critical to being able to be kind of a pioneer or a guinea pig on a new system, and just to mitigating risk in general, right? And now that's not very efficient, but that brings up another set of problems, which is how do we manage all these complex dependencies? Okay, so that's just some high-level thoughts. I guess I'm talking more than I expected. So I'll reiterate what I said about strong scaling. I won't say much more about it. There have been a number of studies on this. It's just something to keep an eye on, and it's affecting a handful of the projects. And I think there are ideas and solvers that are going to minimize the impact of this. So I won't say much more about that. I wanted to give just a couple of exemplars just to illustrate the first point that I made, which is it's just so much more than the notion of porting a code. The number of people, the amount of expertise involved, and the number of levels that people have to work on things. And I'm going to show my Neutron bouncing around. So Steve Hamilton gave me this example from Oak Ridge, and one way of doing Neutron Transport, each of these are independent neutrons. The beautiful thing about they're dumb. They just bounce around until they get absorbed, but they don't interact with each other. And the fact that they don't interact with each other makes it a very easy thing to parallelize, especially if you're doing 100 billion neutrons in a simulation. You have all of the parallelism that you'd possibly need. And this runs very well on CPUs, and the codes were built exactly the way that this simulation showed, which is each core would take a batch of particles and they'd simulate the full history from the birth to the death of the particle. And it would parallelize easily, and it would perform by some standard well, although it's not flop intensive at all. But on a GPU, this doesn't work well. So it doesn't work well on a GPU because it's a MIMD thing. It's not a SIMD thing. Each of those particles is undergoing a different set of instructions as it's carrying out its trajectory, right? So that means thread divergence. It's not a natural fit for the GPUs. So one thing you can do, which is very difficult, is you can entirely invert the algorithm. I should also say not only is it a poor fit for that reason, but the entire code is a loop. there's no little numerically intensive loop. The entire code is, for a particle that goes 1 to 100 billion, do this 50,000 lines of code, which are all the complex physics interactions that dictate what the particle is going to do next. So the probability of collision, probability, the angle, the energy of the reflection, whether it's absorbed, whether it fissions, how many fission neutrons, and so forth. Okay, so you could totally change the algorithm. You could eviscerate the code. So you better be sure that you're going to want to run on this machine, because if you do it, you could do it differently, which is you could do one event at a time. So you can move all the particles just to their first collision. And when you do that, you can sort them by event type. And you could take event types, you can create vectors of them. And those vectors you can process as a single instruction, multiple data artifact, right? Now this looks much better on GPUs. But it's not just like you rearrange a kernel. I mean, you've really changed your entire code. Okay, well, the team led by Steve Hamilton went from history-based over here to event-based. But then it was many more things. It was event-based. It was having to have much smaller kernels to increase occupancy, doing lots of little tricks. And eventually, they marched way up this curve. They were able to get a factor maybe of 20-something on Summit compared to their very well-tuned code on an Intel CPU. So just the number of years it took to do this, the number of people with different types of expertise was kind of a good exemplar of how difficult and involved this can be. In my last minute, I'll say one other one. This is Danny Perez at Lando. This is a really interesting story. So they're doing molecular dynamics calculations, but they're using MD potentials from quantum chemistry calculations. And they actually build a database of quantum chemistry from the quantum chemistry calculations that they use to fit essentially regression coefficients to potentials. And when these are these U's, and they transform them, they transform them to something that is translation invariant, these B's. But the idea is that I think it's a good example of sort of machine learning combined with classic simulation. Anyhow, they were able to, through a massive effort involving a dozen different people, march up this performance curve that you see to get a factor of 19 performance improvement on the GPU since they started. And I just tried to trace, I guess I don't have time to say because I'm out of time, but the number of people working at the facilities, computer scientists, applied mathematicians, each contributed some idea that gave another one of the jumps on the curve that I just showed, which eventually resulted in the performance improvements I said that made it back into lamps using COCOS, which is a programming model that is part of ECP software technology that Doug will tell you about. So I kind of showed you the number of components that went into something that looks like you just ported it and sped it up. The number of collaborators and the amount of time. It was a very good exemplar. And it's all just say, in the end, they got a factor of 90 times the mirror baseline. That's our one code that has surpassed the FOM threshold already, just based off of the Summit architecture. Okay, and he's going to validate the projections, Danny, with a full-scale Summit run soon. Okay, so I'll just say overall, ECP is an extremely difficult project. I've been involved since the beginning. There are many moving parts. We have specialized node architectures, the system software, the programming models, the application level libraries. They're all moving, and they're enabling ambitious science goals with ambitious performance goals. So the early adoption this year, or originally, but now the adoption of the 100 petaflop systems and any test hardware or hardware simulators we have moving toward the exascale systems are really helping with our progress tracking and allowing us to see what's going to be an issue and what technical directions we should take to mitigate any problems. And I'm surprised, and I'm not a salesperson in any sense, but I'm really surprised with how good the progress has been on the Summit architecture. And we need to continue to push early adoption of the exascale hardware, and very important to our success is to ensure the proper balance of domain expertise and performance engineering, because these are science applications and they're led by domain scientists. And our engagement program with the facilities to get the kind of help on performance engineering that enables these results has been a really critical component of our success. Okay, thank you very much.
I think we have time for a couple of questions. What do we have here?
Thanks very much. Great presentation. You mentioned a couple of projects that we're talking about pushing developments into COCOS. Could you talk more about the sort of status of COCOS, or is that a Doug thing?
Well, so it's actually more than a couple. I probably understated it. We have, it might be, I can look it up. We have a database of these dependent. It might be 7 or 8, and it's growing. So I think as people get more bewildered about what they should buy into, they take a harder look at something which is more platform independent, and they've had very good experiences. So the performance results have been really, really good. And you know, I can look up in our database what the number is, but I think it's going to be it is a critical dependency in the project, and it's likely to grow. And you know, I guess I don't have much more to say than that right now, but I probably understated it. Yeah.